Now, there will be cases where the presence of the environment not only act as a support for the main region of the QM region, but it also influence it chemically through polarizing it, and in that cannot be taken by an mechanical embedding. So, an improvement of the mechanical embedding is to include the polarization effect, and the electrostatic embedding happens is that the electrostatic interaction between the two subsystems are handled during the computation of the electronic wave function. In the mechanical wave function, we were calculating the electronic wave function as like it is a free electronic state, the environment is only giving it a mechanical support. So, the charged atoms enters into the QM Hamiltonian as one electron operator. So, this is how the form looks like, where Ri and Rj are the position of the ith electron and atom J, and Hiq is the original one electron operator for the kinetic and nuclear attraction energy of electron 1, and M is the number of atoms that have a Qj partial charge. So, these partial charges actually affect the one electron Hamiltonian. So, it changes the Fock matrix, and as well as so it will change the both the DFT and Hartree-Fock calculations what is done with it. And the electron see these atoms as at special nuclei with non-integer and possibly negative charges. In the case of QM nuclei, generally they have integer charges because we know it has a specific number of electrons. But for these atoms, they actually have non-integer charges, and these charges, why they have non-integer charges, you may think it is unphysical. So, these charges are fitted to describe the electrostatic interaction as accurately as possible. So, although the charges are non-integer, they will lead to correct electrostatic potential. So, what happens in electrostatic embedding is that the interaction between the atoms in the subsystems are handled at the level only. The QM atom enters the self consistent field routine through the charge of the there, and then you diagonalize the augmented force matrix. So, what happens is that you first calculate the region. So, this is the third batch, this is where the calculations are done. After the calculations are done, the corresponding charges are put into the QM region Fock matrix. The Fock matrix is diagonalized. So, the other QM atoms, so you have a guess basis set overlap matrix, then guess a Fock matrix. And what you do here is that the calculations actually comes into the point charges given by the actually comes into the Fock matrix. So, you diagonalize it, you get the energies, if it is converged, you calculate the force, and this force even goes into the two places. First, it goes into the interaction region. This interaction region also passes the information to the region. The region is positions are again changed, and this goes into the QM region, and it goes like this. So, there are three regions which are self consistent to each other, QM atom, the boundaries, and the atom. Remember, electrostatically only the QM atom gets polarized by the presence of the atom. In most of the electrostatic embedding scheme, the atom cannot get polarized due to the QM atom, because there is no polarization term here, and that can lead to some inaccuracies, not so much. And this is how the flow scheme actually goes. Now, question arises whether the polarization induced by these charges are realistic or not. In reality, interaction between the systems are not only due to electrostatic between the charged atom, but also due to polarization, exchange, charge transfer, dispersion, and Pauli repulsion. So, this can actually taken care to an extent by scaling those charges, but it is not a foolproof parameter. In force field, only the combination of atomic charges and Lennard-Jones parameter provides a reasonable description of all these three effects together, albeit in an implicit manner. So, this is a too simplistic picture. So, you are just trying to scale those charges and Lennard-Jones parameter and trying to get all these effects. So, that may not be always possible. You can at best get a good approximation. And part of the interaction due to the polarized region is that already taken care by the Lennard-Jones potential already. So, not only the charges, but also Lennard-Jones potential would need to be reparameterized. So, you cannot just take the charges from a calculation and a Lennard-Jones parameter for the from the force field and put it for the QM. So, you need to do appropriate scaling, and there are different methods for doing this kind of scaling available. The other problem is that the standard atomic charges due to the charge distribution in the risk of overpolarization near the boundary. If I quickly go back into the picture of link atom, so just think of this QM. In the electrostatic embedding scheme, what will happen is that So, this will have its point charges, so this will polarize, but now in the case of link atom method I am also putting a hydrogen atom. So, this charge will also polarize the QM. So, this will now lead to an overpolarization, because not only it gets polarized by this atom, it is also getting polarized by an additional hydrogen. So, this is what is called an overpolarization problem, and you have to somehow deal with it by scaling those overpolarization charges or doing something else, maybe removing those charges, distributing it with other atoms. So, the overpolarization can always be the problem. The second thing is that the point charges, remember, they are classical point charges. So, they may interact or attract or repel the electrons too strongly. So, one is a quantum mechanical, one is a classical, so that is a problem. And this can be a particular problem when the electron density are spilling out into the MM region. And so, what can happen is that some of the wave function can has a long tail which goes inside the MM region. When you are getting the boundary between QM and MM region, you are thinking that these two regions are physically separated. But due to when you use very flexible basis set with large number of polarization or diffuse function or plane wave, what can happen is that the tail of the wave function can get inside the MM region, which can lead to some kind of a physical problem. And this electron spill can be avoided by using a smeared out charges instead of traditional point charges, where the charges follows a Gaussian distribution, and they are generally more effective to remove this kind of artificial problems. But in most of the cases, if you are making a QMM region where the boundary is going through a bond, generally a good idea is not to use the diffuse functions, at least for the atoms which are at the boundary. So, for the atoms which are at the boundary, it is generally a good idea to use a standard basis function without any diffuse function. So, as a test problem, let us calculate the adiabatic electron affinity of this thymine water system, for which we have already calculated the MM and we have the force field parameters. So, first thing we will do, we will calculate adiabatic electron affinity. That means, it is the energy difference between the neutral at optimized neutral geometry and anion at optimized anion geometry. So, although this is only contains 10 water molecules, you may want to optimize something which has, let us say, 1000 water molecules. So, for very large active region, and all of this will be taken as active in these cases. So, for very large active region, the quasi Newton optimization in the internal coordinate can become costly, and the memory requirement will be so high that even to generate those internal coordinate will take more time than calculation of energy or force field, and takes a huge memory. So, generally it is a good advantageous to use the quasi Newton optimization, like the Cartesian based optimization, which is LOPT or LOPT H. So, LOPT H will only optimize the hydrogen, not anything else, because what happens in most of the cases from the crystal structure, you can get the position of the heavier atom and not the hydrogen. So, you have to put the position of the hydrogen by hand. So, you need to optimize them, or you can do the full optimization also. So, what we will do is that we will take the structure, we will optimize the structure using QMM calculation. The optimization will be done using BP86 def2 SVP. We will calculate the frequency, and so we will get the thermochemistry corrections, and then from that one we can actually add it with a higher basis set. So, this is a standard practice that you do the optimization in a lower basis set and add it with a higher basis set single point calculation. So, the single point calculations will be done in BP86 MADEF2 QZVP. We are using this minimally augmented basis set because we are dealing with electron affinity, and electron affinity generally requires basis set with diffuse functions. So, the way we will do it is that I have already have the previously generated PRMS force field file. So, inside this I will generate a QMMM directory, and I will copy the PRMS file and the PDB file. Inside this directory. So, the way we will do here is that we will first do the optimize the anion, and then starting from that geometry I will optimize the neutral, because what can happen is that this actually structure is quite flexible. So, the anion can go to one of the local minima and the neutral will go to the other local minima. So, it may lead to trouble. So, generally a good idea is to first optimize one of them, and starting from that geometry you optimize the other. So, this is how my input file will look like. So, let first with the anion. So, I will make it -1, 2. Let us save it as anion. Okay, let me open it with Chemcraft file. So, from here also you can see that the atom number is up to 15 is actually what should be taken in the QM region. So, it is 1 to 15. So, it should be 0 to 14 in our case, but we can also see it from the Chemcraft file. We can put the number. It is not very easily visible. So, what you should do is show only atom belonging to the subunit and then put the number, and now you should be able to visualize it. So, up to it is from 1 to 15 the atom number should be taken at the QM region. So, now let us submit the calculation. So, by the time this optimization will be done, I have already pre-calculated the neutral and the anion energy of single point only thymine where there is no water molecule. So, I have done the same thing. I have calculated using DEF2 SVP BP86 optimization and single point calculation is MADEF2 QZBP. So, by the time this calculation goes out, let me prepare an Excel file. Show the method, anion single point, anion thermochemistry, anion final, neutral SP, neutral thermochemistry, neutral final, and this is AEA. So AEA always neutral final minus anion final. I want it in EV, so I'll multiply with 27.212. Okay, I have not closed the parenthesis. I think that was the problem. So let us now do the calculation on the thiamine anion, which I have already done. So this is the thiamine anion opt. I'm trying to get this thiamine anion dot output file. This is the thermochemistry correction. This thiamine QZVP single point. This is the final single point energy. This has to be minus. Forgot to copy the so final energy is anion single point plus thermochemistry correction. To do the same thing for the neutral. Here you can see that as it's optimizing, it's going down, the energy is going down actually. And for the neutral, this thiamine dot out. This is the thermochemistry correction. For the neutral, this is thiamine QZVP output file, the single point calculation. I think for the anion by mistake we have copied the we have not calculated the thiamine anion QZPP calculation. So let us calculate it.